Hi, let's continue with our section. In this video, we will summarize large data using the principle component analysis. So suppose that you would like to build a predictor for an individual's expected net fiscal worth at age 45. So there are a huge number of variables to be considered: IQ, current fiscal worth, marriage status, height, geographical location, health, education, career state, age, and many others you might come up with. So such a number of LinkedIn connections or SAT scores. So the trouble with having so many features is severalfold. First, the amount of data which will incur high storage costs and computational time for your algorithm. Second, with a large feature space, it is critical to have a large amount of data for the model to be accurate. That is to say, it becomes harder to distinguish the signal from the noise. So for these reasons, when dealing with high-dimensional data such as this, we often employ dimensionality reduction techniques such as PCA. So PCA allows us to take our features and return a smaller number of new features forms from our original ones with a maximal explanatory power. So in addition, since the new features are linear combinations of the old features, this allows us to anonymize our data, which is very handy when working with financial information, for example. So now is the time to implement it. So let's mount the drive. So I did successfully mount the drive, and then I did CD the content to the Colab notebook. So everything in the Colab notebooks, and we will reuse our previous data. So let's do it. First, we need to import from sklearn dot decomposition. So we'll import PCA, and next we'll import pandas as PD, and then we will have its data equal PD dot read underscore CSV, and then we'll have its file underscore PE underscore headers dot CSV, and now we'll have a save equal comma, and we have is x equal data dot drop, which will have is name, and then we'll have is malware, and then comma axis equal to 1, and then dot to underscore numpy. So this one is result start by importing the necessary libraries and reading in the dataset. So let's run the cell. And now we will standardize the dataset as it is necessary before applying PCA. So we have from sklearn dot pre-processing, and now we will import stand standard scalar, and now we'll have it x underscore standard dice equal standard scalar, and then we'll have dot fit underscore transform x, and now we need to instantiate a PCA instance. Use it to reduce the dimensionality of our data. So we'll have a PCA equal PCA, and now we have PCA dot fit underscore transform, and then we'll have a x underscore standardize, and now we will assess the effectiveness of your dimensionality reduction. So now we have a spring, which will be the PCA dot explain underscore variance underscore ratio underscore, so PCA dot explain underscore variance underscore ratio. So now let's run the cell. So we did successfully reduce our perform the dimensionality reduction, and this is our result. So now let's talk how does it work. So the first is we start by reading our data set and then standardize here as in the recipe on the standardizing data, and it is necessary to work with standardized data before applying PCA. So we now instantiate a new PCA transformers instances. So and use it to both learn the transform fit and also apply the transform to the data set, which is the fit transform. So here, and in step 4, we analyze our transformation. So in particular, note that the elements of PCA explain variance ratio indicate how much of the variance is accounted for each direction. The sum is 1, indicating that all the variance is accounted for if we consider the full space in which the data lives. However, just by taking the first few directions, we can account for a large portion of the variance while limiting our dimensionality. So in our example, the first 40 directions account for 90% of the variance. And now we will sum. So we have the sum, and then we got PCA explain ratio. So we will sum on the first 40, which we will have is 0 to 40. And now let's run. So we got around 90, 0.9. So this means that we can reduce our number of features to 40 from 78 while preserving 90% of the variance. So we have a 90% of the variance, and our number of features is 40, and we reduce it from 78. So the implications of this are that many of the features of the PE header are closely correlated, which is understandable as they are not designed to be independent, so they are correlated, and because that they are not designed to be independent. And that is all in this video. So I hope you successfully perform the PCA, the sum of the PCA explain variance ratio, and also you get the assess the effectiveness of your dimensionality reduction. And that is all in this video, and I will see you in the next video.